guys, and welcome to a new video. In this video we are going to talk about the harmonic oscillator, and the video will be a bit different compared to the others because we are not going to solve any exercise, but it will be a bit more theoretical, but I hope that you will enjoy it. So first of all, we can define a harmonic oscillator, any system that satisfies the following equation. So the second order derivative of the position x of the system with respect to time plus omega 0 x equal to 0. Okay, so as I said, in this case x is the position, so x is obviously a function of time. Here we have the second order derivative, and then here we have a linear term, and omega 0 here is the angular frequency of the system. Let's point out the fact that in this case we are considering an ideal oscillator because we do not have any force F proportional to the velocity, so we are not considering any damping force F proportional to the velocity of the system in this case. Okay, so this equation comes basically from the second law of the dynamics, so from the equation F equal to m times a, where a in this case is written as the second order derivative of the position with respect to time, as we wrote here. And the equation basically describes the effect of a force F which is proportional to the deviation of the system from the equilibrium. Position, that in our case is x equal to 0. Okay, so a classical example of a harmonic oscillator is the string. So we can consider the first example where we have a force F which is minus k times x. So again, x is the position of the system and k is the elastic constant of our string. We know that F is equal to a m times a, and in this case we have minus k times x equal to m, and here a, as I said, can be written as the second order derivative of the position with respect to time. So we end up with this equation, and we can divide by x and move this term to the right side of the equation. So from here we can write that the acceleration times k over m, we divided by m, times x equal to 0. Okay, so as you can see, this the form of the equation is the same as we saw previously. In this case we have that omega 0 is k over m, so from here we can say that the angular frequency of the system is k over m under square root. And from omega 0 we can also calculate the period of the system by 2 pi over omega 0. So that means that basically the period of the string of this simple string depends only on the mass of the of our system and the elastic constant of the string. Okay, so this is an example. Another example. Another example of the harmonic oscillator is the pendulum. So we can consider a pendulum where we have basically a mass m, which forms a angle, let's call it theta, with respect to the vertical axis, and we assume that theta is small, so theta is less than 1. So here the force acting on the mass m is minus mg sine of theta. Okay, so we know that again m times a is equal to this force, but in this case we know that a, the acceleration, can be written as the radius of the of our let's say trajectory. So that can be named d. So in this case the radius is basically the length of the of our string. So from here we can say that a is equal to d times the angular acceleration alpha, but alpha can be written as the second order derivative of theta with respect to time. Okay, so from here we get md, the derivative of theta with respect to time, the second order derivative, and then we have the force. Now we can say that sine of theta, since theta is small, is basically theta. So from here we can cancel the mass and write that the second order derivative of the angle plus g over d times theta is equal to 0. So as you can see, here we basically get the same kind of equation, the equation of a harmonic oscillator, and in this case we get omega 0 squared, which is g over d, and from here omega 0 is g over d under square root. Okay, so we saw two different examples. The harmonic oscillator is also is actually widely used in physics. It is also used. It is also present in quantum mechanics, for example. Okay, so as we said, the general equation of a harmonic oscillator is this one, where omega 0 is the angular frequency, and we know that the general solution of this equation is a function x, function of time, or can be also theta in the case of the pendulum, for example, but the general solution is an amplitude a times sine, and the angle is omega 0 times t plus the phase phi, where basically a and phi depends on the initial conditions of the system. In fact, here, for example, we can also calculate the velocity as a function of time of the system, because we know that the velocity is the derivative of x with respect to time. So if you derive this times omega 0 cosine of the same angle. Okay, so this is the function representing the velocity of the system, and here we can, for example, set the initial time, let's say at 0. So that means that x at time t0 will be a sine of omega 0 t0 plus phi, which will be simply a sine of phi. And the velocity at time 0, so t0, will be a times omega 0 cosine of phi. Okay, so these are basically the initial conditions of the system. The position at time 0 is this one, and the velocity is this one. And from here it is quite easy to see that, for example, phi will be the tangent to the minus 1 of omega 0 times x0 over the velocity at time 0, because if you call this value v0 and this value x0, we have that x0 is a sine of phi, and then we have that v0 is a omega 0 cosine of phi. And from here you get that, for example, a is x0 over sine of phi. So from the second equation you get that v0 is equal to x0 over sine of phi times omega 0 cosine of phi. Okay, and from here you basically you get the result that we wrote here. So theta depends only on omega 0, so the angular frequency, the initial position, and the initial velocity. And if you also calculate a, you will get that a, so the amplitude is x0 squared plus v0 squared over omega 0 squared and the square root. So as well, a depends only on the initial position and velocity, so depends on the initial conditions and the angular frequency of the system. Okay, so these were the constants, the A and V of the system, so the constants of the solution that depend on the initial conditions. As far as the energy of the system is concerned, we know that in general the force of the harmonic oscillator will be minus m omega 0 squared x times x. For example, in the case of the string, we saw that omega 0 squared was k over m. So from here you can see clearly that the force of the string, so the force acting on the system, is minus k times x. But in general we can write the force of the force acting on the harmonic oscillator in this kind of form. Okay, so this form shows clearly that the force depends only on x, depends only on the position. So that means that the force is conservative, and that means that the force, if the force is conservative, it means that we can write that the force is minus the derivative of the potential energy with respect to the position. Okay, and this means that the potential energy can be calculated from the force considering the integral of x, as we said, the function of the position in the x from 0 to x. Okay, so here we can call it, for example, x prime. Okay, so that means that the potential energy in our case will be 1/2 m omega 0 squared x squared. Okay, so the potential energy of the harmonic oscillator is this one, is a function of the position, and in particular it is a parabola. We know that obviously the kinetic energy is 1/2 m the velocity squared, so that means that the total energy, let's call it ET, will be the potential energy plus the kinetic energy EK, and as we said, this will be 1/2 m omega 0 squared and x squared plus 1/2 m v squared, but this one can be written as 1/2 m omega 0 squared x squared plus v squared over omega 0 squared. But we know that this one is x 0 squared plus v 0 squared over omega 0 squared, because since the force is conservative, the total energy will conserve. So since the total energy depends only on this term, basically it means that these terms will be the same at t equals 0 or at any time t different from 0. So it means that here we can substitute x with x0 and v with v0, but this is the expression of the amplitude squared. So that means that the total energy can be written as a function of the amplitude of the solution, basically.